Hello there, Mr. Sutton here, bringing you the Algebra 2 4-3 lesson on dividing polynomials. In this one, we will be dividing polynomials using long division, and after that, in part 2, we will figure out how to divide using something called synthetic division. To start things off here, before we try dividing polynomials, maybe we should make sure we know how to divide just regular numbers. So pause the video and give this one a shot. Alright, so we're dividing 654 by 7. If I'm using long division, which maybe you haven't used since you were in elementary school, but here it is again, we put the number we're dividing into, which is called the dividend, inside a little house, and we put the number that we're dividing by, which we call the divisor, outside the house. So we have dividend divided by divisor, and I only mention that because we're going to be using those words again. Alright, so first step here, we see how many times 7 goes into 6. It doesn't go in at all, so we see how many times 7 goes into 65, and that's going to be 9 times. And then once you've got a number up here, you have to multiply that back by the divisor, so 9 times 7 gives us 63. Then we have to subtract the product we just got from the dividend, or the parts of the dividend that apply to it here. So we're subtracting 63 from 65 to give us 2. After we've done that subtraction, we bring the next number in the dividend down to be with the difference that we just got here. So this gives us now 24. And then we start the cycle of divide, multiply, subtract all over again until we run out of numbers to bring down. So 7 goes into 24 now 3 times, and then 3 times 7 gives us 21. Subtracting that gives us a grand total of 3. And this 3 we call our remainder. So writing this little R3 up here is certainly one way to express it. But if we wanted to be a little fancier, we could write our answer as 93 and 3/7. That's what this remainder actually means. It means you've got a piece of this 7 that you were dividing by. So it's always remainder over divisor if you want to write it like this, which we're going to be doing with polynomials. Now that we've seen long division with constants, we're going to see how that process can be applied to divide one polynomial by another using long division. So we're going to start this in kind of the same way we did with the constants. We're going to put our dividend in a little house, and the divisor is going to be outside the house. So here is dividend house and divisor kind of knocking on the door saying, let me in, let's do some division. So how do we actually start this? Well, if we were doing just constants, we would divide whatever was out here as far in as we needed to go with this dividend. How does this work with these weird polynomials? So the trick here is we're not going to divide this entire y plus 2 into here. What we're actually going to do is we are going to divide the lead term of the dividend, this y squared, by the lead term of the divisor, by y. So we're only dealing with 2 terms at a time. We're not trying to do everything at once. So how many times does y go into y squared? Well, that might be kind of a weird question to ask, so maybe another way to ask this is, what is y squared if I divide that by y and simplify? Well, y squared divided by y, you would just cancel a y and get y. Now, where would that y go? It's going to go above the y to the first power column here. This is one thing about long division, is we've got things separated by columns, and the columns are all based on exponents. So we have the squareds, the first powers, and the constants, and if we had higher exponents, we would have more columns to represent those as well. So we've got our initial step done here. So now what do? Well, when we got a number up here before, we multiplied it by the divisor, and that's actually what we're going to do here. We're going to multiply our quotient that we got here by our divisor. But now we're going to multiply by the entire divisor. That's the trick here. We're going to distribute this y to the y in the plus 2. So y gets multiplied here. Y times y is y squared. Again, this goes under the y squared column. And then y times 2 is going to be a plus 2y. And at this point, just like we did with regular numbers, we are going to subtract what we got here from the dividend. So put a big minus here. So the y squareds are going to cancel out completely. And now we have 5y minus 2y, which is going to give us 3y. And at this point, after you've done your subtraction, we just bring down the next term and start the process over. We're going to bring down the next term and repeat. So this plus 5 comes down here to be with the 3y. So if you think you might have the hang of this process, feel free to pause the video and see if you can finish this one off, get the rest of the quotient, and maybe figure out the remainder while you're at it. All right, let's see how that went for you. So we're going to start the process here by dividing the y. We're just, again, doing the lead term into the 3y. How many times does y go into 3y? Well, 3y divided by y is just 3, and that's going to go in our constants column up here. Then multiplying 3 back out, we've got 3y, and then 3 times 2 is going to give me a plus 6. Now we subtract that. 3y's cancel. We have just 5 minus 6, which is negative 1. So we have our quotient up here of y plus 3, so that's part of the answer, and the remainder can be added on as a fraction over the divisor. So here's what that would look like. I would just do a plus and then a fraction, negative 1 over this y plus 2 that we divided by. And that's actually what was going on our last problem as well, when we had the, let's see, what did we end up with for an answer? So here was that last problem we did. We had 93 and 3/7. This is really 93 plus 3/7. We still have addition going on here, we just don't bother writing the plus sign. So what we've done here with this remainder is just kind of a more general case that covers everything, constants and variables. Because these long division problems are, well, long, we're only going to do one more before we end this part of the lesson. But before I have you try this one out, mostly on your own, there is one little hint that we're going to give you, because if you mess this next little piece up and then do all that work with this beginning part wrong, you're going to get kind of frustrated. So here's the thing that we need to be careful of. Notice our exponents in the dividend. We've got an x to the fourth. We've got an x to the third. And, we skip to x to the first. Where's that x squared that we would expect in there? It's not in there. It doesn't have to be. But here's the trouble. When we were doing long division on that last one, we said there were different columns for each power that was in the problem. Well, if we're missing one of the powers, we actually need a placeholder 0 for those missing terms. Otherwise, things are not going to line up the way they need to for us to get the correct answer. So when I rewrite this in my little house format here, I'm going to have 2x to the fourth plus 3x cubed plus 0x squared to hold that missing place there. And then I have the rest of it, plus 5x minus 1. So with this in mind, pause the video and see how far you can get with this long division. All right, so starting things up, we have x squared going into 2x to the fourth. Again, we're doing lead term into lead term. 2x to the fourth divided by x squared. We're just subtracting the exponents there. So that's going to be 2x squared. And I'm going to put that in my x squared column up here. Now we're already glad that we have this placeholder 0. Otherwise, where would I put an x squared? I'd have no place to put it. So now multiplying this back out by the divisor, 2x squared times x squared is 2x to the fourth. Times 3x gives us 6x cubed, and then we have 2x squared times 2 giving us a plus 4x squared. Now I have to subtract all this. 2x to the fourths are going to cancel completely. 3x cubed minus 6x cubed is negative 3x cubed, and 0 minus 4x squared is going to be negative 4x squared. Just like before, we're going to bring down the next term, so that's plus 5x comes down here, and we start the process over. So now we're doing x squared into the lead term here of negative 3x cubed. Negative 3x cubed divided by x squared is going to give us negative 3x to the first, which I'll put up here in my x to the first column. Multiplying that back out now, negative 3x to the first times x squared is negative 3x cubed. Negative 3x times 3x is negative 9x squared. And then negative 3x times 2 gives us negative 6x. All right, let's subtract this stuff now. Negative 3x cubed cancel, and this should always happen, by the way. Because you're doing lead term into lead term, you should always get something that's going to give you the lead term again when you multiply it back out. And now we've got negative 4x squared minus negative, so plus 9x squared. That's going to be 5x squared. And then we have 5x minus minus, so plus 6x, giving us 11x. And now we can drop down that last term there, negative 1. Now we have x squared going into 5x squared, and that's going in 5 times. Multiplying it back out, we've got 5x squared, and then 5 times 3x is 15x, and then 5 times 2 gives us a plus 10. Subtracting all of that, 5x squareds cancel. 11 minus 15 gives us negative 4x, and then negative 1 minus 10 gives us negative 11. So when the dust settles, we have a quotient of 2x squared minus 3x plus 5, which I'll write down here, plus we have our little remainder piece. This is going to be negative 4x minus 11, all of that over x squared plus 3x plus 2. So this is quite the crazy looking remainder here, but we've got to write it because otherwise this wouldn't be a completely accurate division. So that is it for this part of the lesson. It wouldn't be a lesson on division if we didn't divide the lesson itself up into 2 parts. So pause the video, do some long division practice, have lots of fun with that, I'm sure, and then come back and we'll show you a faster way to do some of these problems. Some of them you'll still need long division for. Welcome back. Thanks for joining us for part 2 of polynomial division. In this one, we're taking a look at synthetic division. Synthetic division, we'll just give a quick definition here, is just a shortcut for dividing polynomials, like we've been doing, by x minus k. So things in this binomial linear sort of format. Now it is important to note that synthetic division really does only work for things that are in this form, like this y plus 2 here. If we were trying to divide by something to the second or third power, this would not work as well. There's a way to get it to kind of work that we'll talk about after we go through an example, but it's kind of tedious, so it's almost not worth it if you're dealing with any other situation. But this is a common situation, so let's figure out how this works. First step we're going to have to do is to write down the coefficients of the dividend. So coefficients of y squared plus 5y plus 5. We have an invisible 1 for the y squared, a 5 for the 5y, and a 5 for the 5, which is really just 5y to the 0. And if any of these terms were negative, we would have to bring the negative down with our numbers that we wrote as well. So don't forget those negatives. Next step, we're going to write the k from the x minus k. So this is basically whatever zeroes out your divisor. And if you're having trouble figuring out what that's going to be, you can just set your divisor equal to 0 and solve. So for example, if we set y plus 2 equal to 0 and then subtract 2 to solve for y, that would give us a k value of negative 2. So once I figured out k, what do I do with it? Well, I'm going to write it off to the side here in a little sort of half box. You could make it a whole box if you wanted. It doesn't really matter. And also, you might see it if you look at some math textbooks. Sometimes they put it down a few rows. As long as you've got it separated from everything else, that's the important piece. So what are we going to do with this negative 2? More on that later. One other thing we're going to do is we're going to leave a little bit of room for a second row, and I'm going to write a line separating the second row, what's going to be the second row, from the third row. Okay. So my next step is I'm going to take this first coefficient that I wrote and I'm going to bring that down to the bottom row. So I'm just going to bring the 1 down here. Once I have a number in the bottom row, my next step is going to be to multiply this k that I set aside here by whatever is in this bottom row. And I'm going to put the product from doing this multiplication in the middle row. So we're doing negative 2 times 1, and that's going to give me negative 2, which I'm going to put 1 column over in this middle row right here. Next thing we're going to do is we are going to add the top and the middle row together and put the sum in the bottom row. So we're doing 5 plus negative 2, and that's going to be 3. We're going to put the 3 down here. Now, when I brought this 1 down initially, you could even think of this as just having an invisible 0 in the second row to start with, and you're just doing 1 plus 0 to get this 1, if that helps you be consistent. Now, once we've got this number down here, we're essentially just going to keep repeating the process. Multiply k by the bottom row, add the top and the middle row, just keep repeating that as needed until we run out of numbers. So let's just keep going. We've got negative 2 times 3, that's going to be negative 6, that goes in the middle row. And then we have 5 plus negative 6, that's going to be negative 1 in the bottom row. Once we've run out of numbers, what do all these numbers down here actually get for us? So the first bottom row numbers, the 1 and the 3 here, everything except that last number, those first numbers, those are the coefficients of your quotient. And your quotient's going to start one exponent lower than the dividend did because you basically are dividing y squared by y, so that should knock your exponent down by 1. So this 1 here really represents 1y to the first power. And this 3 just represents 3. It goes down by 1 exponent as you move to the right here. Now how about this 1? What does this 1 give us? So that last bottom row number is the remainder. So we could write plus negative 1 over y plus 2 to get that remainder piece. Now if you're wondering if synthetic division actually works or if I just kind of made this all up, saw it in a dream or something, well, check it out. Let's go back to what we saw before when we did this division the long way. So here is the long division version of what we just did with synthetic division, and if you look, we notice that we get y plus 3 plus negative 1 over y plus 2. So there we go. Proof that synthetic division works. Now, if you're like me, you might look at the last problem that we did, this crazy long division problem at the end of part 1, and you might be like, well, could I do this with synthetic division? Because this is awfully tedious. Well, the answer is actually on this one you could, but you'd have to be a little bit clever about it. So you can only divide by linear factors one at a time. If you could factor x squared plus 3x plus 2, and you can factor it into x plus 1 and x plus 2, you could divide this whole thing using synthetic division by x plus 1, get an answer, and then divide that answer by x plus 2. So you could do two synthetic divisions if you wanted to do it without using long division. But that is its own kind of tedious, and also, what if you can't factor your divisor? Then you're stuck with long division anyway. So moving on now to example 4. This is another synthetic division problem. Pause the video and see if you can apply the process we just learned to synthetically divide this thing. All right, so let's walk through it now. Let's write out our coefficients. We've got 3, negative 7, 2, and 3. And again, notice that negative came down here because that was in the original. Our box number now, what zeroes out the divisor, is going to be 5, because 5 minus 5 is 0. So box number over there. Make a little line for dividing the second and third rows. And we bring down our first coefficient. And then we're multiplying our box number, our k value, by the bottom row. So 5 times 3 gives us 15. Negative 7 and 15 is going to be 8. 5 times 8 gives us 40. 2 plus 40 is 42. And 5 times 42, maybe a little mental math here, I think that's 210. And then 3 plus 210 is giving us 213. So one of the nice things about synthetic division, and we'll get the quotient and all that in a minute, but one of the nice things about this is if you get really good at it, it is possible to do a lot of these just completely in your head. I would still write out your work, but the mental part of this is a possibility. So now what's our quotient going to be? We've got a 3. This represents 3x to the second power. Again, it's going to be 1 power lower than we started with up here. And then we have an 8x plus 42 plus 213 over x minus 5. Here's another synthetic division problem for you. Pause the video and give this one a shot, but be careful with this one. All right, let's see how this one went. So we have our coefficients. We have a 1, a minus 6, And not a 22. We've actually got a 0 in there because we're missing an x squared. So just like with long division, with synthetic division, you need the placeholder zeros, which makes sense because this is based entirely off of long division. So now we have a 22 and a 40. Box number is going to be a 4 because 4 minus 4 is 0. So we bring down our 1 times 4 is 4 plus negative 6 gives us negative 2. 4 times negative 2 gives us negative 8, and then 0 and negative 8 is still negative 8. 4 times negative 8 is negative 32. And by the way, if you were missing this 0, you would have had a negative 8 going under the 22, so that would have changed things quite a bit. So this is now going to be negative 10 down here, and then 4 times that is negative 40. 40 and negative 40 gives us 0, so a remainder of 0. This is our first time getting that. So we've got 1x to the third power minus 2x squared minus 8x to the first minus 10. And we don't need to write plus 0 over x minus 4 because, well, that's just 0. Now, one thing that is kind of worth noting about this, if you get a remainder of 0, it actually means that the thing you just divided by, this x minus 4 in this case, is a factor of this polynomial. And if you wanted to, you could actually split this polynomial up into x minus 4 times all of this quotient stuff. That's actually going to be very useful later on in this chapter. For our next problem, we're going to take a look at an application of synthetic division, namely synthetic substitution. So for this problem, they're asking us to use synthetic division to evaluate this function at the value x equals negative 4. So what is this about? I mean, no one said anything about evaluating functions. So it turns out there is a theorem that is involved in this called the remainder theorem. The remainder theorem basically says that if you're dividing a polynomial f of x by x minus k, the remainder that you get from that is going to equal f of k. The remainder you get is going to be whatever number you would get by plugging k into the function. So in this context, what this means is you can actually find f of k, or f of negative 4, by finding the remainder, dividing by x minus negative 4. So we're just using synthetic division to simulate the process of plugging something in. So pause the video and actually do that, and let's see what we get. Okay, so if we're doing synthetic division, we would have coefficients of 5, negative 1, 13, and 29. We didn't miss any placeholder zeros here. And our box number, our k value, is going to be this exact number, negative 4. So if we bring down our first coefficient, we got 5. Negative 4 times that's negative 20, plus negative 1 is negative 21. Negative 4 times that is 84. Plus 13 gives me 97. Let's see, negative 4 times that, a little trickier. 4 times 100 would be 400. This is going to be like 12 less than that. So negative 388. Yep. And then if I add that to 29, well, let's see here. 30 plus this would give me negative 358. So this is going to be negative 359. There we go. So this means that f of negative 4 then is going to be negative 359. So that was neat. That was kind of interesting. And you might be wondering, why not just do like why not just do like 5 times negative 4 cubed minus negative 4 squared, and why not just plug it in normally? Well, there is an advantage to this synthetic substitution kind of stuff. The big advantage is, notice we didn't use any exponents as we were doing this. It was all just adding, multiplying, just basic operations, no exponents needed. So if you have a lot of big exponents and you're plugging in a fairly large number, that could be a pain to do with normal function evaluation. This is just another way to get there. We're going to do one more example, and this one's a little bit crazy. This problem, they're asking us to find the remainder when we divide 4x to the 736 plus 5x to the 97 minus 20 by x plus 1. So if you're doing this with synthetic division, Your first coefficient is 4, and your next coefficient is going to have to be, well, 0, right? Because there's no x to the 735. And the coefficient after that would also be 0. There's no x to the 734 listed here. And there's a whole bunch of placeholder zeros, hundreds of placeholder zeros. This would be a huge pain with synthetic division. But the remainder theorem could actually help us out here. So we saw that if we were trying to do f of k, we could just find the remainder by dividing by x minus k, and that would be the same thing. Well, it works in reverse. It turns out you can find the remainder by finding f of k, by finding f of the thing that you had being subtracted from x in your factor. So with that in mind, see if you can apply this in order to solve the problem and get the remainder without doing synthetic division. All right, so what we need to do here is we need to do f of k. In this case, k is going to be -1 because that zeroes out x plus 1. So we're doing f of -1, which means we're plugging -1 in for these x's here. Now this might seem kind of ridiculous with these supersized exponents, but let's think about this. We're just multiplying a bunch of 1's together, right? And if I'm multiplying an even number of 1's together, -1's, that means I'm going to get a positive value out of that. This is just going to be 4 times +1, or just 4. If I have an odd number of negatives, that comes out to an odd answer. So this is just 5 times -1, which is just -5. And that -20 is still kind of there along for the ride. So 4 minus 5 would be -1, minus another 20 would be -21. So this is actually the remainder you would have gotten with all those placeholder zeros. So at this point, we have finished everything in this lesson with no remainder. Until next time, Mr. Sutton signing off.